As we deal with redox reactions, we're dealing with the transfer of electrons. So the substance that gets oxidized gives away its electrons to another substance that actually gains them, going through a process we call reduction. This is where we get the idea of redox, reduction, oxidation reactions. But since this is all about the transfer of electrons, what it means is we need to actually know where electrons are over the course of a reaction. And we use a system that we call oxidation numbers in order to help us find electrons over the course of a reaction. Now, oxidation numbers themselves are kind of like a little bookkeeping system, and that system allows us to actually track where they were at the start as reactants and where the electrons move to as the substances become products. This idea of oxidation numbers, though, is a little bit confusing, and so what I wanted to go through is the origin of where they actually come from and understanding why oxidation numbers actually exist at all. And in order to understand this, we are going to take a look at a molecule we have seen tons over the course of studying chemistry, and that is water. So, as we take a look at a molecule of water, we end up seeing something that looks like this, right? We have this bent structure, we have our hydrogens connected to our oxygens, and to understand the idea of oxidation numbers, we also need to understand one of the most important fundamental concepts in the structure of a molecule, and that is the electronegativity. Now, in case you don't remember what electronegativity is the idea that some substances or some atoms pull on electrons more than others. So it is essentially how strongly an atom pulls electrons towards itself. Now, we actually have a table of electronegativity, and that table you can actually take a look at in order to see that every substance has its own specific electronegativity. Now, using this chart, we could take a look at the two substances in water, the two atoms. We have oxygen, which has an electronegativity value of 3.5, and hydrogen, which has an electronegativity value of 2.1. Using this scale, we could take a look at this idea that oxygen, with its electronegativity of 3.5, and hydrogen, with its electronegativity of 2.1, give an electronegativity difference of 1.4. That's a pretty high electronegativity difference, and helps us understand that this is what we would call a non-polar, or actually, sorry, this is a polar, my bad, covalent bond, meaning that this bond is not sharing electrons equally. Since oxygen wants the electrons more, along this bond, the oxygen is actually going to pull electrons towards itself. And the hydrogen is then going to get just a tiny negative charge or positive charge. The oxygen has essentially kind of gained an electron, not fully, but kind of. And so it has an extra electron hanging around it. But the same thing is going to happen over here. This hydrogen is going to lose its electron to the oxygen as the oxygen literally pulls it towards itself. That's going to give the oxygen just a slight negative charge as well, and a slight positive charge to this hydrogen. When we talk about the oxidation numbers, what we're really talking about is where electrons are spending a lot of their time. And so for hydrogen, we would say in this molecule, it has an oxidation number of +1. And that's because each of our hydrogens are actually giving away an electron to this oxygen. Not completely, but partially, and good enough that we can actually count it as doing that. The oxygen, on the other hand, is actually going to get an oxidation number of -2, meaning it's gained 2 electrons. And it's gained 2 because it's actually pulling electrons from both hydrogens, gaining a little bit of a negative from each one. This is where oxidation numbers come from, is the idea of electronegativity. Different elements pull on electrons with different strengths, meaning that some elements will actually gain electrons, whereas other elements will give them up, leading to different amounts of positives and negatives in different molecules. Now, you may be worried if you are trying to think about, oh, I need to find oxidation numbers. Do I actually have to go around and calculate all of the electrons and where they are and the electronegativity differences and draw the Lewis structures? No, you definitely do not have to, because what I'm going to show you in my next video is that we have a set of rules, and that set of rules around oxidation numbers we can actually use to help us figure out the oxidation numbers of every single substance in every single molecule. And so we can just apply them, but they're all based off of this idea of electronegativity inside of the Lewis structure of every molecule. So thanks for watching and learning about oxidation numbers, and I'll see you in my next video as we talk about the rules to calculate them.